Hey everyone and welcome. So today, we're gonna go on a pretty wild journey. We'll start with something you do every day, a single keystroke. And by the end, we'll be looking at the future of technology itself. We're gonna pull back the curtain on the fundamental building blocks that make our entire digital world tick. So let's jump right in.
All right, let me ask you something. You press the letter A on your keyboard and boom, it pops up on your screen. But have you ever stopped to think about what happens in that split second? I mean, what actually happens in between? How on earth does a machine, a thing that only understands on or off, 1 or 0, possibly comprehend something as human as the alphabet?
Well, the magic behind it is a process called encoding. And honestly, the best way to think about it is like a universal translator. It takes our language, our symbols, everything we understand, and converts it into the only language a computer speaks, the binary language of zeros and ones. It's the absolute first step for any kind of communication with a machine.
This slide right here breaks it down perfectly. When you press A, the keyboard doesn't send a little A down the wire. Nope, it sends a signal that gets mapped to a standard number. So in a super common standard called ASCII, the capital A is always number 65. Then that number 65 gets converted into its binary form, 1000001, and that's the language the computer can finally understand and process.
So you see, this whole encoding thing, it's not just a neat trick. It's literally the foundation for all digital communication. Without these shared standard codes, my computer would never be able to talk to your computer. It's the invisible protocol that makes the entire internet, and really all modern computing, even possible.
Okay, so check this out, because this is where it gets really cool. We're not just talking about one letter at a time. A whole word, like data on this slide, gets broken down character by character. Each letter gets its own number, which in turn gets its own binary code. It just becomes a long string of ones and zeros. Every single piece of text you've ever read on a screen went through this exact process.
But here's the thing, right? The world is a whole lot bigger than just the English alphabet. Early standards like ASCII were pretty limited, and that's why we have Unicode. It's a massive, universal standard that aims to give a unique number to every single character from every language on Earth. I mean, this was a game changer, making technology truly global and accessible for everyone. Okay, so we've got the data sorted. The computer understands our letters and words as binary code. But now what? How do we actually tell it what to do with all that data? How do we make it solve a problem for us?
Well, that's where the algorithm comes in. And look, if encoding is our translator, think of an algorithm as the recipe. It is a clear, step-by-step set of instructions, and if the computer follows them exactly, it will solve a problem. It's just like baking a cake, right? There's a start, an end, and a specific number of steps you have to follow.
And you don't just, pull a recipe out of thin air. There's a process, a really logical one. First, you gotta really dig in and understand what you're trying to solve. Then you come up with your plan, your algorithm. Only then do you start writing the actual code. And finally, you test it, break it, and fix it over and over until it works perfectly.
Now, one of the coolest ways to actually see an algorithm is with a flowchart. And this example is just perfect because it's something we've all dealt with. The lamp doesn't work. So, is it plugged in? No? Well, plug it in. Yes? Is the bulb burned out? It's a visual map of the thinking process. So simple, so smart.
So if a flowchart is the visual blueprint, there's also a text-based version called pseudocode. And yeah, pseudo just means fake, so it's basically fake code. It's a way to sketch out the logic of your algorithm in plain English. The whole point is to focus on the steps without getting bogged down in all the picky rules and syntax of a real programming language.
All right, so every good chef knows a recipe isn't just a list of steps, right? You need ingredients, you need bowls, you need somewhere to put everything. It's the same in programming. Our algorithms need ways to hold and organize the data they're working on, and that's where data structures come in. They're basically the programmer's toolbox.
And a perfect example of one of these containers is a Python list. Honestly, the shopping cart analogy is spot on. It's an ordered container for your stuff. The key thing is that it's mutable, which is a fancy way of saying you can change it, add things, take things out, move them around. It's just a super flexible and powerful way to hold your data.
And get this, using these tools doesn't have to be complicated. If we have our list, our shopping cart, and we want to add something to it, we just use a simple command like this, mylist.append new item. That's it. That's all you need to tell the computer, hey, take that shopping cart and toss this new item in. Simple as that.
Okay, let's pause for a second. We've got our data, translated through encoding. We've got our recipes, the algorithms, and we've got our toolbox of data structures to hold everything. These are the core building blocks. So, now for the really fun part. What can we actually build with all this? Where does this take us?
For starters, we can build artificial intelligence, AI. This isn't sci-fi stuff. This is the magic that's running in your pocket right now. It's how your map app figures out the fastest way to work, avoiding traffic. It's algorithms that can learn from data, make decisions, and solve problems, just like we do.
Then there's the Internet of Things, or IoT. This is what happens when we take those same building blocks and stick them inside, well, everything. Your smartwatch, your thermostat, your car, they all become little computers connected to a giant network, all sharing data and working together. And as you can imagine, all these smart devices talking to each other, they create an absolute tsunami of information. We call it big data. And to get our heads around it, people often talk about the 5 V's. There's the sheer volume of it, the incredible velocity it's created at, the variety of data types, the veracity, meaning we have to be able to trust it, and finally, value. And that last one, value, that's the whole point. That's the holy grail, finding the useful knowledge hidden in all that noise.
So when you step back and look at the big picture, you can see how it all connects. We literally went from the most microscopic detail, a single binary digit, all the way to these huge futuristic ideas that are shaping our world. And it's all built on the same core principles.
It's amazing, right? It all starts so small, with translating one letter into ones and zeros. That lets us handle data. Then we create a recipe, an algorithm, to tell the computer what to do with that data. We use a toolbox of data structures to keep it all organized. And from that simple foundation, we build the entire modern world. AI, the IoT, everything. So look, this stuff isn't just theory. These are the literal building blocks of our digital world, like the atoms and molecules of technology. They're the tools, and the only real question left is, what are you going to build with them?